NENOMATICA, where mathematics meets YouTube excellence. Today, we're going to explore an interesting algebraic identity, the sum of cubes of two terms. This identity allows us to express the sum of two cubes, a cubed plus b cubed, as a product of two factors. We want to prove the following statement. For all real numbers a and b, the product of a plus b and the quantity a squared minus a b plus b squared equals a cubed plus b cubed. Let's prove this identity step by step. We'll start with the left side of the equation and expand it to show that it equals the right side. Let's begin our proof. First, we'll write out the left side of our equation. Now, we'll apply the distributive property to expand this expression. We multiply each term in the first factor by each term in the second factor. Let's expand this expression step by step. First, we multiply by each term in the second factor. Let's continue expanding. We distribute a to all terms in the first parentheses and b to all terms in the second parentheses. Now, let's simplify each term. We get a cubed minus a squared b plus ab squared plus b a squared minus a b squared plus b cubed. Next, let's combine like terms. Notice that we have negative a squared b and positive b a squared, which are the same since multiplication is commutative. Also, we have ab squared and negative b squared, which will cancel out. Let's highlight the terms that will cancel each other. After combining like terms, we get a cubed plus b cubed. Let's see what happened. We have a squared b and b a squared, which are the same term. Since one is positive and one is negative, they cancel out. Similarly, ab squared and b squared cancel each other out. So we're left with just a cubed plus b cubed. Therefore, we have proven that for all real numbers a and b, the product of a plus b and the quantity a squared minus ab plus b squared equals a cubed plus b cubed. Let's see a practical example of using this identity. Suppose we want to calculate the sum of 8 cubed plus 1 cubed. Using our identity, we can rewrite this as the product of their sum and a polynomial. Let's solve this step by step. First, 8 plus 1 equals 9. Then, we calculate 8 squared minus 8 times 1 plus 1 squared. 8 squared is 64, 8 times 1 is 8, and 1 squared is 1. So we have 64 minus 8 plus 1, which equals 57. Finally, 9 times 57 equals 513. We can verify this. 8 cubed is 512, plus 1 cubed, which is 1, gives us 513. We need to find the value of this expression x plus 2, multiplied by x squared minus 2x plus 4. Looking at this expression, we can recognize the pattern of our sum of cubes formula, where is x and b is 2. Let's apply the sum of cubes identity. The rule states that a plus b multiplied by a squared minus a b plus b squared equals a cubed plus b cubed. Now, let's apply this formula to our expression. First, we substitute x for a and 2 for b in the right side of our identity. This gives us x cubed plus 2 cubed, which equals x cubed plus 8. Let's verify this by expanding the left side of the equation. When we multiply x plus 2 by x squared minus 2x plus 4, we would get x cubed minus 2x squared plus 4x plus 2x squared minus 4x plus 8, which simplifies to x cubed plus 8, confirming our answer. Let's move on to our second example. We need to find the value of this expression x plus 3, multiplied by x squared minus 3x plus 9. Again, we can recognize the pattern of our sum of cubes formula, where it is x and b is 3. Let's apply the sum of cubes identity again. The rule states that a plus b multiplied by a squared minus a b plus b squared equals a cubed plus b cubed. Now, let's apply this formula to our second expression. First, we substitute x for a and 3 for b in the right side of our identity. This gives us x cubed plus 3 cubed, which equals x cubed plus 27. Again, let's verify this by expanding the left side of the equation. When we multiply x plus 3 by x squared minus 3x plus 9, we would get x cubed minus 3x squared plus 9x plus 3x squared minus 9x plus 27, which simplifies to x cubed plus 27, confirming our answer. Let's try a quick challenge. Use the sum of cubes identity to find the value of the expression 2 plus y multiplied by 4 minus 2 y plus y squared. Pause the video and try to solve it yourself. The answer is 8 plus y cubed. Let's see why. Let's summarize what we've learned today. We learned the sum of cubes identity, which states that a cubed plus b cubed equals a plus b multiplied by a squared minus ab plus b squared. We saw how to apply this identity to solve two examples: x plus 2 multiplied by x squared minus 2x plus 4, which equals x cubed plus 8, and x plus 3 multiplied by x squared minus 3x plus 9, which equals x cubed plus 27. Try to practice this formula with different values for a and b to become more familiar with it. We need to multiply the expression 2x plus 1, multiplied by 4x squared minus 2x plus 1. We can apply the sum of cubes identity, where a equals 2x and b equals 1. Let's substitute these values into our formula. We have a plus b, which is 2x plus 1, multiplied by a squared minus ab plus b squared. Now, let's verify what a squared is. A squared is 2x squared, which equals 4x squared. Next, let's calculate ab. ab is 2x times 1, which equals 2x. And finally, b squared. b squared is 1 squared, which equals 1. So the second term becomes 4x squared minus 2x plus 1. This matches our original expression, confirming we can use the sum of cubes identity. Using our identity, the result is a cubed plus b cubed. A cubed is 2x cubed, which equals 8x cubed. And b cubed is 1 cubed, which equals 1. Therefore, the product equals 8x cubed plus 1. Now, let's look at our second example. We need to multiply the expression 2a plus b, multiplied by 4a squared minus 2ab plus b squared. We can apply the sum of cubes identity where a equals 2a and b equals b. Let's substitute these values into our formula. We have a plus b, which is 2a plus b, multiplied by a squared minus ab plus b squared. Now, let's verify what a squared is. A squared is 2a squared, which equals 4 squared. Next, let's calculate ab. ab is 2a times b, which equals 2ab. And finally, b squared remains as b squared. So the second term becomes 4 squared minus 2ab plus b squared. This matches our original expression, confirming we can use the sum of cubes identity. Using our identity, the result is a cubed plus b cubed. A cubed is 2a cubed, which equals 8a cubed. And b cubed remains as b cubed. Therefore, the product equals 8a cubed plus b cubed. In summary, we've learned how to use the sum of cubes identity to multiply specific binomial expressions. The key points to remember are: first, identify if your expression matches the pattern of plus b times a squared minus ab plus b squared. Second, determine what a and b represent in your specific problem. Third, substitute those values into the formula to get a cubed plus b cubed. We solved two examples. In the first example, we found that 2x plus 1 times 4x squared minus 2x plus 1 equals 8x cubed plus 1. In the second example, we found that 2a plus b times 4 squared minus 2ab plus b squared equals 8a cubed plus b cubed. This formula can save you a lot of time compared to multiplying out the expressions directly. We want to simplify the expression. Open parenthesis 3a squared plus 2b cubed, close parenthesis times, open parenthesis 9a to the fourth minus 6a squared b cubed plus 4b to the sixth, close parenthesis. This might look complicated, but we can apply our identity if we identify the right terms. Looking at our formula, we need to recognize what are our a and b values. If we match this to our pattern, we can see that a equals 3a squared and b equals 2b cubed. Let's verify that this is indeed the correct pattern match. If it equals 3a squared, then a squared equals 9a to the fourth. And if b equals 2b cubed, then b squared equals 4b to the sixth. Also, the middle term should be negative a times b, which is negative 3a squared times 2b cubed, which equals negative 6a squared b cubed. So indeed, our second bracket is exactly equal to a squared minus ab plus b squared with our substitution of a equals 3a squared and b equals 2b cubed. Now that we've confirmed our pattern match, we can apply our special product formula. According to our rule, the expression equals a cubed plus b cubed. So, substituting our values, we get 3a squared cubed plus 2b cubed cubed. Let's simplify this. 3a squared cubed equals 3 cubed times a to the sixth, which equals 27a to the sixth, and 2b cubed equals 2 cubed times b to the ninth, which equals 8b to the ninth. So our final answer is 27a to the 6th plus 8b to the 9th. Let's move on to our second example. We want to simplify the expression, open parenthesis x squared plus 1 close parenthesis times open parenthesis x to the 4th minus x squared plus 1 close parenthesis. Again, we need to match this to our special product formula. Looking at the pattern, we can identify that it equals x squared and b equals 1. Let's verify our pattern matching. If it equals x squared, then a squared equals x to the 4th. And if b equals 1, then b squared equals 1. Also, the middle term should be negative a times b, which is negative x squared times 1, which equals negative x squared. So indeed, our second bracket is exactly equal to a squared minus ab plus b squared with our substitution of it equals x squared, and b equals 1. Now we can apply our special product formula. According to our rule, the expression equals a cubed plus b cubed. So, substituting our values, we get x squared cubed plus 1 cubed. Let's simplify. This x squared cubed equals x to the 6th, and 1 cubed equals 1. So our final answer is x to the 6th plus 1. Let's summarize what we've learned about this special product formula. The formula a plus b times a squared minus a b plus b squared equals a cubed plus b cubed allows us to quickly evaluate certain types of algebraic expressions. We need to expand and simplify the following expression. X plus 3 squared times x squared minus 3x plus 9 squared. Let's start by rewriting the expression to better see what we're working with. We can use brackets to emphasize that we're dealing with the product of two square terms. Now, we need to find the product inside the square brackets. To do this, we'll use a special formula for multiplying binomials with a common term. The formula states that when we have a plus b times a squared minus ab plus b squared, this equals a cubed plus b cubed. Now, we need to expand the square of x cubed plus 27. When we square a binomial, we can use the formula a plus b superscript 2 equals a superscript 2 plus 2a plus b superscript 2. So, x cubed plus 27 squared equals x cubed squared plus 2 times x cubed times 27 plus 27 squared. Let's simplify this expression. X cubed squared equals x to the 6th power. 2 times 27 equals 54. So 2 times 27 times x cubed is 54x cubed. And 27 squared equals 729. So our final answer is x to the 6th power plus 54x cubed plus 729. Let's move to another example. We need to expand and simplify. X plus 2 times x squared minus 2x plus 4 times x cubed minus 6. Again, we'll start by rewriting the expression to better see what we're working with. Let's focus on the first two terms. Like before, we'll use the special formula for multiplying binomials with a common term. A plus b times a squared minus ab plus b squared equals a cubed plus b cubed. In our case, a is x and b is 2. Now, we need to multiply these two binomials together. When multiplying two binomials, we can use the FOIL method. First, outer, inner, last. Or simply distribute each term from the first binomial to each term in the second. Let's simplify this expression. X cubed squared equals x to the 6th power. 8 times x cubed minus 6 times x cubed equals 2 times x cubed. And negative 6 times 8 equals negative 48. So our final answer is x to the 6th power plus 2x cubed minus 48. Let's summarize what we've learned. When expanding polynomial expressions, we can use special patterns and formulas to simplify our work. For expressions like a plus b times a squared minus ab plus b squared, we get the sum of cubes, a cubed plus b cubed. When squaring binomials like a plus b squared, we use the formula a squared plus 2a plus b squared. And when multiplying two binomials, we can use the FOIL method to distribute terms. These strategies help us tackle complex polynomial expressions efficiently. Thank you for watching. Keep practicing these techniques to become more proficient with polynomial expansions and simplifications. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.